There's an object moving through our solar system right now that is doing something no natural comet is supposed to do, glowing an unnatural shade of blue as it rounded the sun, sprouting a tail that points in the wrong direction, and accelerating away from us in a way that doesn't match the physics of anything we've cataloged before. And one of the most credentialed astrophysicists in the country is on record saying he can't rule out that it isn't a comet at all, even as the overwhelming majority of his own colleagues studying the exact same data have reached a very different, far more conventional conclusion. Stick around, because I'm going to walk you through exactly what James Webb and a small fleet of other telescopes have actually confirmed about the interstellar object, called 3I/Atlas, why some of what they found is genuinely strange, and why the scientific community is split on how alarmed anyone should actually be. And if you want more of these deep dives into real published research instead of recycled headlines, go ahead and subscribe. Now, because there's a lot more coming out of the far edges of our solar system. To understand why this particular object has generated so much genuine scientific debate, you first need to understand what makes it different from literally everything else astronomers have ever pointed a telescope at. Every comet that regularly passes through our solar system was born here, inside the same cloud of gas and dust that formed our sun and its 8 planets roughly 4.5 billion years ago. An interstellar object is something else entirely. It formed around a different star, drifted through the emptiness between stars for potentially billions of years, and then, purely by chance, its path happened to carry it through our solar system. Astronomers have only confirmed 3 of these objects in all of recorded history. The first, nicknamed Oumuamua, showed up in 2017 and behaved so strangely, tumbling through space without any visible tail at all, that it kicked off years of scientific argument that still hasn't fully settled. The second, Borisov, arrived in 2019 and looked much more like an ordinary comet. The third, discovered on July 1st of 2025 by a network of automated sky-scanning telescopes and officially designated 3I/Atlas, is the one currently generating the most controversy, because unlike its 2 predecessors, astronomers caught this one early enough to actually study it in detail while it was still active, and what came back wasn't entirely straightforward. It's worth understanding just how much unfinished business Oumuamua actually left behind, because it's part of why 3I/Atlas gets scrutinized so intensely today. Oumuamua showed its own non-gravitational acceleration back in 2018, moving away from the sun slightly faster than gravity alone predicted, without ever showing the visible tail of gas and dust that normally explains that kind of effect in a comet. That mismatch led to a genuinely unresolved scientific debate, with some researchers proposing invisible, undetected outgassing as the explanation, and others, including Loeb, proposing the object could have been an extremely thin artificial solar sail reflecting sunlight in a way that produced the same acceleration without visible dust. That argument was never definitively settled one way or the other before Oumuamua sped out of observable range entirely. And it's part of the reason any new interstellar object showing similar acceleration patterns draws this much immediate attention from researchers on both sides of that older, still open disagreement. The first anomaly showed up almost immediately, and it involves the direction of the comet's tail. Every comet that warms up near the sun is supposed to develop a tail pointing away from the sun, because sunlight and the outward pressure of the solar wind physically push gas and dust particles in that direction. That's not optional. It's basic physics, and it's one of the most reliable, predictable features of cometary behavior that exists. But as 3I/Atlas approached the sun, observers using the Hubble Space Telescope and ground-based observatories documented something different, a bright, elongated glow pointing toward the sun instead, nicknamed an anti-tail. Researchers have continued tracking this feature for months, and as recently as December of 2025, it was still visible in new images, even as the comet moved farther from the sun and closer to Earth. If you're finding this as unsettling as a lot of people online clearly have, drop a comment and let me know, because it genuinely helps me figure out what other space stories are worth covering next. Now, before this starts to sound like something out of a science fiction film, it's worth saying clearly that an anti-tail by itself isn't actually unprecedented. Astronomer Jason Wright at Pennsylvania State University pointed out that similar sunward glows have shown up before on ordinary solar system comets, including a well-documented case involving Comet Kohoutek back in the 1970s, caused by larger dust grains that are heavy enough to resist being swept backward by radiation pressure the way finer dust and gas normally are. Most of the researchers studying 3I/Atlas agree that this specific explanation, a concentration of larger, slower-moving dust particles, most likely accounts for what's being observed, and NASA itself has stated publicly that the object poses no danger and behaves consistent with a natural comet. Not every scientist studying the data is fully convinced that's the whole story, though, and this is where things get genuinely interesting rather than simply spooky. Avi Loeb, a professor at Harvard and the director of its Institute for Theory and Computation, has spent months publishing detailed technical analyses arguing that several features of 3I/Atlas deserve closer scrutiny before anyone declares the case fully closed. In a paper posted in December of 2025, Loeb proposed an alternative explanation for the anti-tail, suggesting it could represent a trailing swarm of smaller objects lagging behind the main body, a byproduct of the same unexplained acceleration that's become the second major point of debate surrounding this object. That acceleration is the part of this story that even mainstream researchers acknowledge is worth taking seriously, even if they disagree with Loeb's more dramatic interpretation of it. As 3I/Atlas approached its closest point to the Sun in late 2025, tracking data compiled by NASA's own Jet Propulsion Laboratory registered what's called a non-gravitational acceleration, meaning the object sped up and changed course slightly in a way that simple gravity alone couldn't fully account for. For an ordinary comet, this kind of behavior is actually well understood and expected. As ice on a comet's surface warms and turns directly into gas, that outgassing acts like a very weak natural rocket thruster, nudging the comet's trajectory in small, predictable ways. Nearly every comet that's ever been tracked closely enough shows some degree of this effect. What made 3I/Atlas's version noteworthy is the specific pattern researchers measured, an acceleration that scaled with distance from the Sun in a way that closely mirrored the Sun's own gravitational pull, along with additional components pushing the object sideways relative to its orbital path. The actual numbers involved help put the size of this effect into perspective. According to Loeb's own published calculations, the measured acceleration amounted to roughly 9 times 10 to the negative 7th astronomical units per day, squared in the radial direction alone, an almost impossibly small number in absolute terms, but one that stood out because of how precisely it appeared to track the inverse. Square pattern associated with gravity itself, rather than fading off in the more irregular way outgassing typically produces as a comet's ice supply gradually depletes. That specific mathematical relationship is part of what caught researchers' attention in the first place, since ordinary cometary outgassing, while common, doesn't usually scale quite that cleanly. In April of 2026, Loeb and a collaborator named Tony Scarmato published a follow-up analysis using several additional months of Hubble imaging, applying a specialized image processing technique to strip away the comet's circular glow and isolate finer structural detail. What they found was a set of 3 distinct jets emanating from the nucleus, spaced almost perfectly around 120 degrees apart from each other, in addition to the primary anti-tail jet, already pointed toward the Sun. Loeb was careful to frame the finding cautiously in his own write-up, noting explicitly that these jets could just as easily represent pockets of ice arranged symmetrically across the surface of an otherwise ordinary natural object as they could represent anything engineered, and that the outflowing gas and dust from any of the 3 jets would produce the same kind of rocket effect thrust, regardless of which explanation turns out to be correct. Loeb has been the most vocal in pushing this data further than most of his colleagues are willing to go, at one point suggesting publicly that the pattern could theoretically be consistent with a spacecraft using a maneuver to intentionally gain speed as it departs the solar system, rather than simply venting gas passively. He has also pointed to the object's unusual blue coloring, observed as it passed closest to the Sun, as another data point worth investigating, speculating that it could reflect anything from an unusual natural gas signature to, in his more speculative framing, an artificial light source. It's important to be direct about where the broader scientific community stands on these specific claims, because it's a genuinely lopsided debate. Researchers reviewing the same tracking data have pushed back hard on how confidently that non-gravitational signal can even be measured in the first place, noting that pinning down the precise position of a fuzzy, glowing comet is difficult enough that the uncertainty in the measurement may be larger than Loeb's analysis accounts for. The overwhelming consensus among planetary scientists actively studying 3I/Atlas is that outgassing from natural ices remains by far the simplest and best supported explanation for everything observed so far, and Loeb himself has continued to frame his alternative readings as hypotheses worth testing against the data rather than conclusions he's certain are correct. This is where Webb's contribution to the story actually matters most, because spectroscopy, the technique of breaking light apart to reveal exact chemical composition, is precisely the kind of evidence that can settle a debate like this one. Using its near-infrared spectrograph in August of 2025 and later its mid-infrared instrument in December, Webb measured the precise gases pouring out of 3I/Atlas as it warmed near the Sun. What it found was carbon dioxide in overwhelming abundance, making up roughly 87% of the gas being released, along with water, carbon monoxide, methane, and even trace amounts of nickel, a full and coherent chemical fingerprint entirely consistent with an unusually old carbon dioxide-rich natural comet, and not remotely consistent with anything resembling exhaust from propulsion or manufactured materials. That detected nickel signature briefly generated its own round of speculation online, since nickel is obviously associated with metal alloys here on Earth, but researchers studying cometary chemistry have pointed out that trace nickel and iron vapor have been detected in ordinary solar system comets before as well, released through entirely natural photochemical processes involving nickel-bearing minerals, not anything indicating artificial construction. There's a physical detail worth addressing directly too, since it's been a recurring talking point in online discussion of this object: its sheer size. Early brightness measurements led some researchers to floating estimates for the nucleus that sounded genuinely enormous. Comparisons to the footprint of an entire borough of a major city circulated widely online. More careful follow-up imaging from the Hubble Space Telescope, using a technique that carefully subtracts a modeled version of the surrounding coma to isolate the faint signal of the actual solid nucleus underneath, placed the upper limit on the nucleus diameter at roughly 3.5 miles across, with researchers noting the true size could be considerably smaller depending on how reflective the surface material actually is. That's a large comet by solar system standards, but well within the range of sizes seen among known comets and asteroids, not an anomaly requiring an exotic explanation on its own. There's also a piece of independent evidence that has nothing to do with chemistry, acceleration, or size at all, and it comes from an entirely different scientific instrument built for a completely different purpose. In mid-December of 2025, during the comet's closest approach to Earth, the Breakthrough Listen program used the Green Bank telescope, one of the largest steerable radio telescopes on the planet, to scan 3I/Atlas across a wide range of radio frequencies, specifically searching for any signal that might indicate an artificial transmission. The search came back completely clean, no candidate signals of any kind. If 3I/Atlas really were some kind of active technological device, a dedicated radio search at close range during peak visibility would represent one of the most sensitive opportunities available to detect it, and it found nothing. There's also a much older independent line of evidence that lines up with the natural explanation, and it comes from simply tracing the object's incoming trajectory backward through the galaxy. Researchers led by Matthew Hopkins at the University of Oxford calculated the specific path 3I/Atlas was following before it ever entered our solar system. And that path traced back to a region of the Milky Way called the thick disk, a broader, older portion of the galaxy home to stars that are, on average, significantly more ancient than our own sun. Separately, isotope measurements taken directly from Webb's spectroscopy of the comet's water and carbon dioxide, led by researcher Martin Cordner at NASA's Goddard Space Flight Center, pointed toward an object that likely formed somewhere between 10 and 12 billion years ago, potentially older than the sun itself. Having a completely independent trajectory calculation and a completely independent chemical isotope analysis, both pointing toward the same ancient origin, gives researchers real confidence that whatever this object is, it's exactly what it appears to be on its surface. An extraordinarily old, naturally formed comet that happens to be passing through at a moment in history when our telescopes are finally good enough to study it up close. It's worth pausing to explain why this level of public disagreement, playing out mostly in real time on blogs and social media rather than quietly through peer review, is actually somewhat unusual for planetary science. Most scientific debates about comet composition or trajectory happen slowly, through journal submissions and conference presentations, largely invisible to anyone outside the field. What's different about 3I/Atlas is that one of the researchers involved has chosen to publish his ongoing analysis publicly and rapidly, in near real time, generating enormous public attention along the way, while the broader planetary science community has continued working through the same data, using more conventional, cautious channels. That mismatch in pace and public visibility is part of why this particular object has become such a lightning rod. Not because the underlying data is necessarily more unusual than anything astronomers have seen before, but because the disagreement over how to interpret it has played out so publicly and so quickly. None of this means every question about 3I/Atlas has been fully answered. Some of the isotope measurements carry real uncertainty. The precise cause of the anti-tail is still being refined, even among researchers who agree it's a natural feature. And the non-gravitational acceleration, while almost certainly explained by outgassing, hasn't been modeled down to every last detail. Genuine open questions remain, and that's normal for an object this rare and this difficult to study during the brief window. It's actually within reach of our telescopes. What's already reasonably well established, though, across chemistry, trajectory, radio silence, and isotope analysis alike, is a coherent picture of an ancient natural comet, not a coherent picture of anything artificial. 3I/Atlas, has already passed its closest approach to both the Sun and Earth and is now heading back out into interstellar space permanently, following a hyperbolic trajectory that guarantees it will never return. Every additional observation researchers manage to squeeze in before it fades out of instrument range adds one more piece to a debate that's likely to continue being discussed and reanalyzed for years, even after the object itself is long gone. It's worth pausing to explain why any of this actually matters. Beyond the obvious appeal of a good mystery, every genuinely new interstellar object represents an almost impossibly rare opportunity, a direct, physical sample of material that formed somewhere else in the galaxy entirely, at some other point in cosmic history, drifting close enough for our instruments to study it before it's gone forever. Getting that analysis right matters both for understanding this specific object and for building the kind of careful, verified toolkit researchers will need to properly evaluate the next one and the one after that, as detections become more frequent in the years ahead. A hasty conclusion in either direction, dismissing a genuine anomaly too quickly, or overselling a data point that doesn't hold up to scrutiny, risks getting in the way of that longer-term goal. It's also worth noting that the Vera Rubin Observatory, a powerful new ground-based survey telescope that recently began its full operational scan of the southern sky, is expected to dramatically increase how often objects like this one get detected going forward, potentially finding several interstellar visitors per year instead of one every few years. The rough rate that gave us Oumuamua, Borisov, and 3I/Atlas across nearly a full decade. That means debates like this one, over ambiguous acceleration data and unusual surface features, caught during a single, narrow observing window, may become considerably less rare in the years ahead, and considerably easier to resolve once researchers have more than a single object's worth of data to compare against. So, what does all of this actually add up to? A comet, unlike anything cataloged before, old enough to predate our own sun, chemically and dynamically strange enough to generate a genuine, serious scientific argument about how to interpret it, and thoroughly enough studied across 5 separate instruments and research teams that the overwhelming weight of evidence points toward something entirely natural, even while a handful of specific anomalies remain worth watching closely. If stories like this one, grounded in real published research and honest about where scientists still disagree, are what you want more of, subscribe to this channel and turn on notifications, because there's a real chance the next interstellar visitor generates just as much debate as this one did. Thanks for watching, and I'll see you in the next one.